Okay, so today I'm going to be going over uh, a really basic-ish overview of reinforcement learning, which I think is one of the coolest subfields of deep learning. Actually don't think it fully falls into a subfield of deep learning. It's kind of like a bubble that encompasses like a lot of things, but there are parts of it, and especially parts of it that I'll talk about now, that definitely exist within deep learning. The cool stuff, a lot of the cool stuff that I've learned, definitely does. So it's like this is a whole like separate like really interesting topic. I'll be giving like what I've learned on it, but I'm full disclaimer right now, this is like a huge thing. Like to claim I'm teaching reinforcement learning right now is like claiming I taught everyone all of machine learning before. It's simply not true. Like there's whole like years of courses dedicated to it. But I'm gonna definitely be giving like a what's cool about it, what can you do with it, and some of like the intro algorithms in this field. So definitely like, maybe this might require some note taking, I'm not sure. But however you learn. I just think this is one of the coolest topics ever. So yeah, this, yeah, definitely this. So let's start off with what is reinforcement learning, shortened to RL. If you see the words RL, it's usually reinforcement learning. So it's the formalization and study of how we can have these autonomous agents, robotic or, in silico, operate, yeah, I guess right here, in real or simulated environments. So basically, like, how can we have this, like, thing, this, like, object move and interact with the environment, and how can we, have it accomplish, like, tasks for us, right? And the application specifically of deep learning when it comes to reinforcement learning is basically making them more powerful. Like, how can we make it so that these agents don't just, solve a maze, but can grab items with their hands, understand complex tasks, learn to walk and run, for example? Here's a little video I'll play. Yeah, so if any of you have ever felt like this, maybe you are a reinforcement learning agent. So this is pretty cool though, because even though yes, it's ridiculous, this agent learned how to walk on its own, as in it was not shown what walking looks like. It was given the constraints of limbs as humans have, and then it was told to reach an objective, which in this case seems to be those balls that show up around the map. And it was just said, go towards that direction, right? And then it learned how to walk, or it figured out that this is the most optimal way to reach its goal. I think yeah, well, this is still a work in progress field, right? So anyway, there's a lot of cooler things you can do. Oh, next slide, please. Yeah. So one of the most amazing uses of deep reinforcement learning, at least that I know of, is the programs AlphaGo and AlphaGo Zero. So one of the world's best Go players, Lee Seal, was put up against AlphaGo, which is a reinforcement learning agent trained to play the game of Go, which, disclaimer, I have never played myself, but based on the many articles I've read online and what the papers I've seen, it is at least as complicated as chess. The state space is much bigger. The amount of positions and plays you can make is bigger, but I don't know the rules. But it's complicated, obviously, because this was a huge deal. So essentially, they put AlphaGo up against Lee Sedol, and AlphaGo won 4-1. So yeah, this is pretty incredible. And what was especially incredible about it was this thing called Move 37, which is right there highlighted. Now, to me, and maybe to most of you, unless you're like, top level Go players, this may not seem like much. But essentially, that move right there was very what you would call like off strategy to what humans would play. Um, at least according to like what Lee Sedol said and some other pro Go players said. They said that this was a very interesting move. Some people even called it beautiful and creative. And I think that's really amazing because, you might think of a reinforcement learning agent as something that simply just follows like a certain like greedy policy, like, oh, let me just take the most optimal action here. Let me just act the best, turn left when I see a wall, turn right when I see another wall, something like that to solve a maze. But if you apply the idea of reinforcement learning to really complex games, you can get really interesting strategies that come out of it. And more recently, and I wish I had included this, Bean Kim came and talked to us about some of the research that she was doing, and she's big in interpretability. So basically, what happened was they had a chess bot essentially train grandmasters on some quote unquote superhuman moves. So there is some paradigm of how like chess is played, but when you train a reinforcement learning agent, it is not necessarily bound by um, what do you call it, human precedence in terms of what it can or cannot do or what is a good move, right? So it's allowed to be creative, and it can do thousands of millions of calculations per second. So it explores this huge space and comes up with really interesting moves and strategies that Bean Kim and her team essentially took and distilled somehow to grandmasters so that they can learn from those like incredible superhuman moves. So reinforcement learning isn't just, it doesn't just exist in your computer or in a robot. It can really teach you cool things because you're basically having a computer explore these ideas. And I guess I can continue. Oh yeah, there's a movie or I guess documentary on it, but I think it's on like Prime Video. So check that out as well if you're interested in this kind of stuff. It'll tell you more about how that works. Oh yeah, and another cool thing is this. I didn't put it on here again, but alpha tensor. Has anyone heard of alpha tensor by any chance? So like the short form of it is basically they turned matrix multiplication into like a gamified problem called Tensor Game, and then had a reinforcement learning agent play that game, and its goal was to complete a matrix multiplication in the fewest number of multiples possible, and it was basically able to break through what was currently like solved by human mathematicians for some 4 by 4 matrix multiplication. So it found a faster algorithm. So usually maybe you're like theory professors are like, oh, look at this, all this like crazy math on the board, and we prove that this is the lower bound. Well, or they might say like, oh, this is we require brute force search to like search like or find this solution. Reinforcement learning essentially, I won't say it fully breaks that idea, but it can start to find solutions to problems that you can think of as being only brute forceable, right? Or maybe like hasn't been like proved to be unsolvable yet. You can throw, if you have enough compute, you can throw this idea at it, and maybe something cool will come out of it. So again, this is all set up for why I think reinforcement learning is cool. So now we're going to go into like a pivot a little bit into like directly some terminology of reinforcement learning. But before we do that, any questions on what I've said so far? Okay, awesome. Oh, yes. So you know what? I thought that for the longest time too. AlphaFold, which is used to essentially estimate the 3D structure of proteins given their amino acid sequences, is not reinforcement learning. Alpha, as a prefix, just means that DeepMind made it, and it's really cool. So yeah, yeah. So AlphaFold, unfortunately, is not reinforcement learning. Although it completely makes sense why you think it was, because it also could seem to be gamified. But based on my research, it doesn't seem like it uses reinforcement learning a lot. So the first two and some of the most important terminologies that you'll definitely hear me like reference and just say, oh no, hold on one second. Where's my backpack? This is a gaming laptop, so it dies in like 20 minutes. Okay, we're back. All right. So we have states and actions. States are essentially a snapshot of the environment that the agent is in at a certain time. So this little I don't know, bubble that you have moving through a maze or something, right? What the state of the maze is, or maybe what the agent can see about that maze, is captured in something called a state. And it's kind of like wishy-washy for good reason. It can represent a lot, like it can be a lot of things. Like if you have a strong enough network, a state could literally just be a screenshot of the game that you're playing right now. In like if you don't have as much compute and you need a simpler thing, say you have a game where you need to balance a pole on some kind of stick and need to move back and forth to make sure that pole stays balanced, the state could simply be the angle of the tip of the pole, the speed at which it's moving, and the position of your cart, basically, right? So those are two examples of state. They basically just capture what is going on at the current moment. And they have to have this property for a lot of like the theory to hold up when it comes to reinforcement learning, which is they have to be Markovian. Essentially, transitions from one state to another do not directly depend on what steps have previously been taken. Now, the funny thing is, even if it is like not fully Markovian, some of the like if you throw a deep reinforcement learning agent at a problem, it might still do fine. But if the process is Markovian and you can capture states that way, the reinforcement learning agent will do a lot better. The easiest example is like maybe you have a state of Pong, right? And you have the ball. You could give the position of the ball, but then you don't necessarily know which direction it's moving. So you could argue that, oh, it has a dependency on where the ball was previously, has a dependency on a previous state to really know what's happening, right? So then maybe instead of giving the position of the ball, you give the velocity of the ball. And that can tell you a little more information and make the state that you capture a little, and I'm using this very, very badly, more Markovian, even though, it's Markovian or it's not. And then you also have this thing, so it's like the transitions from one state to another are influenced by mainly two things. One, just random chance in the environment, and two, actions that your agent can take. So there's one state, right? Like this one screenshot of the ball. Now, if the ball is kind of up in that corner, right, it's going to hit the top, it's going to hit the wall and come back down. No matter what the agent, the paddle does, it's not going to change the trajectory of that ball, right? So for that point, for those points, the state is determined by the dynamics of the environment. But say you can move the paddle left and right to hit the ball. Now your actions have an influence on the state, right? So sometimes they can have an influence on the state and sometimes they don't. It just depends on what game you're playing, right? And then here's the thing I've been talking about, actions. This is a little more intuitive. Basically, it's just like, they're denoted with a subscript with respect to time, which time step do you take this action in, and they're taken by the agent once you give it the state. You basically say, this is what you're looking at right now. Do you want to move left or right, or stay still? That might also be an option, right? And like I said, they often impact the next state. And another thing is, and this is pretty important, a pair of a state and an action. So given a screenshot of the world, and you kind of pick, oh, I want to go left, for reinforcement learning to work, that generally should give you some kind of reward. Some kind of number telling you how well you did. How good was it to take that action, right? Like, say you have an agent that is running towards a cliff and it should turn left onto the road, right? If it keeps going straight and you don't tell it that, hey, there's a cliff coming ahead, stop, 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 well, it's not going to do the right thing. You need to reward it to turn left. Like, hey, the good stuff's over here, take a left. Any questions on states in action so far? Okay, cool. So some more key concepts. I think I've already kind of used these, but I'll just go over them quickly. So you have the agent, which is the thing that's moving through your environment. Any questions on what an agent is? I guess I've been kind of using that word already. All right. Then we have the environment, which is basically what your agent is navigating through. Okay. These should be semi-intuitive, but sorry, yes.
So just for the last slide, in terms of like actions,
Mm-hmm.
The second bullet point, given, the third bullet point, does that mean that oftentimes the reinforcement learning program will try and predict the next move it should take even after this one?
Yeah, so we'll go into exactly what the agent will do. So the question was, will the agent predict future states after seeing like, oh, it's impacted one state? Will it predict the next action it should take in the next one, and so on and so forth? Is that generally your question?
Yeah.
Okay. Sorry if I'm not getting it fully. But I guess my answer is basically wait until I get to the equations. You'll see that there is dependence on what is in front of you, but also some dependence on what lies far ahead. Okay? But that all culminates in an action for the current state. If that makes sense. Yeah. And finally, reward. This is super important. It's a signal that indicates how well that state action pair is. Does you understand what I mean by state action pair? You're in some kind of state, and then you take an action in that state. You move left to right, given like a screenshot of the brick breaker game, and then that tells you like, oh, you did good or you did bad. Like for example, in the previous case, you could have that moving towards where the ball will ultimately end up is like going to give you more reward than if you say, for example, moved way more to the right. Like say moving a little bit to the left gives you a lot of reward. Moving too far to the left gives you no reward, and moving to the right gives you no reward. The agent will start to learn to only move a little bit to the left and hopefully link that to the idea of where the ball will land. And then it'll learn how to play brick breaker. There's some more because reinforcement learning, as you'll see, is just letters and numbers and letters and numbers and everything more. So there's also the idea of a trajectory, which is represented by tau, and it is this first thing over here that I have. It's basically like a sequence of actions that the agent will take. I'm going to start using like little balls and arrows to basically give a higher level overview of like what states and actions are. Like for example, you have the initial position of something. It moves and takes an action and gets to state 1. Then it moves and takes an action to get to state 2, and then so on and so forth. And then there's some final terminal state or something that either kills the agent or tells it accomplished its task. And then you kind of go backwards and say, what did you do to get there? You put that all into like some kind of variable, and that's your trajectory. Okay, so it's a summary of what the agent did to either die or accomplish a task, right? Or you might have some kind of like timer that expires, and if it takes too many moves, then it also dies, right? But it's essentially just a string of like states and actions that the agent took. And then here is where it gets a little more like interesting. We have return, which is the cumulative reward over a trajectory. This ultimately becomes the core element that we want to maximize. So we want to say, okay, here's some trajectory, right? Let's say going to states 1, 2, and 3 was optimal, right? And then maybe there's some states over here, or maybe it's just something. Imagine there's more than just those diagrams, right? And it should have gone over there, but it didn't. It went all the way over there and then died over at the final position, right? So the return of that trajectory won't be very high because the agent didn't do so well, or it didn't accomplish its task, right? And if we slowly tell the agent, hey, that's not the best way to do things, get better, get better, get better, maybe eventually it'll start taking trajectories which have high returns. And those should, if you put the rewards in your environment correctly, correlate with an agent that can solve the problem that you have posed it. For example, a maze or racing on a track, right? That's the idea of return. This is what we're trying to maximize. We want to maximize the return. So not necessarily the reward over one step. Like we're not trying to say get the maximum reward and then jump to the state with the highest reward. If the state with the highest reward is surrounded by like a bunch of lava that like gives you a bunch of like low reward, or it's not worth it or something like that, maybe the agent shouldn't do that. Maybe it should go for the trail of like rewards of level 5, that's safe, and it will definitely get them. So and then it's for the agent to figure out which one is the best path to follow.
How is reward projected beyond just the next step? Or does it is each like branch considered at every step?
So usually what will happen is you will make some kind of game that will calculate the rewards for you. Like it's not, well, you could like handcraft per state in action. Here's the reward, but then you already solved the problem, right? So like if you had brick breaker, for example, maybe you'd calculate the reward as like a function of how close you are to the ball, right? And then that would encourage the agent to just be close to the ball because that's where the highest reward is. And then by proxy, it solved the problem of playing the game, right? That's an important concept called reward shaping. If you're making an environment for an agent to play in, you need to make sure that the rewards are placed in such a way that the agent can actually solve the problem. If you're rewarding bad behavior, it's going to be a bad agent. Yeah. Any questions on that so far? Yeah. I've never, well, I feel like depending on, I don't know enough to make a strong claim on that. That's pretty cool. But like you could argue that maybe one of the actions the agent could have taken was clicking the pause button. The pause button maybe extended the game, but didn't stop the external timer that was giving it reward. So it found out that when it clicked that pause button, I just get consistent reward with no stops. And then so, it does that a couple times, then it realizes this button equals me winning. So then it just hits the pause button. Like I'm not sure how they set it up, but that could be one of the explanations. Any other questions? Okay. This is where everyone should wake up. This is the hard part. Amea's laughing over there. So I tried to make it easier. This is probabilistic equation hell. But we're gonna start off with there's this resource called Spinning Up in Deep RL by OpenAI. I think it's wonderful. It's one of the resources I've linked inside the reinforcement learning unit. We're going to take this big paragraph that last quarter, I guess spring quarter, I just showed and talked about, and I'm going to give a lot more of an intuitive understanding of this problem. But let's read that top text first, right? So, oh, you know what I just realized? I never went over this last thing right here. No one caught that? Oh, come on, guys. Okay, so we have a discounting factor as well, and this ties into the return. Basically, you want to consider rewards that are right in front of you, but also things that are very far off into the future. But the things that are really far off into the future, you want to consider a little bit less. So basically, as you move through time, you just have this gamma that usually sits at 0.99 or 0.95, something like that. And then it's a put to the power of your time step. And then basically that is used as a multiplier for the reward at that time step, making it so that the reward progressively falls off as you look too far into the future, right? So that just tends to help with convergence, and it also makes it so that the agent acts a little more reasonably and doesn't just wait for 20 years and then go for some goal. I don't know. It basically makes it so that it tries to take some kind of actions consistently without waiting too long. Any questions on that? Okay. So then I'm going to talk about that top text, ignore the equations. I'm going to go through them step by step. So whatever we choose to determine return, right? The equation I give previously was infinite horizon discounted return. And whatever the choice of the policy it says here, policy being essentially policy and agent, for the purposes of this lecture, you can consider them pretty similar, right? The goal is to select a policy or an agent that acts in a certain way such that you maximize your expected return whenever you're put in that environment, right? So like I said before, we are trying to maximize the return, okay? So we want to pick an agent that will take actions such that its return overall is very high, right? So the first thing is this. How do we calculate, which is on the left right here, the probability of a trajectory tau given a policy pi? Well, say you have I have a series of coin flips or something, right? Say a coin flip and a dice roll. I flip a coin and it's heads, and I roll a dice and it's lands on a 6, right? What's the probability of that happening in sequence? Someone raise their hand. There you go, right? So you multiply them together, and that tells you the probability of that sequence of events happening, right? So that's what we're kind of doing here. You can see that P, a rho sub 0, I'm just going to say P sub 0, and then in parentheses there's a S sub 0. That is the probability of starting at your starting state, right? Say, for example, there's 2 starting states. You can either start on this half of the screen or this half of the screen. And maybe the agent just by random chance was initialized to this half of the screen, right? That will give us the probability rho O P O of S0. So that's our starting state, right? And let's say that we have a 75% chance of ending up in that little blue circle, right? And the other 25% of the time we happen on the other side, okay? So that takes care of that first part, right? We have the probability of us being initialized somewhere. And usually if you create your environment, you'll know that. You'll be like, oh, 1/10 of the time they start at this part of the maze, the other 10th of the time they start at this part of the maze, you'll know this. And then for the rest of the equation, let's say we start like having our agent actually explore. It goes to the next blue state, but there was also an option of that orange state that it didn't go to, right? And then it goes to that next blue state, but there was the option of that orange state it didn't go to. Now let's look at what we have, right? Let's say that agent's transition probability from this state to that state was around, 25%, right? And then the transition probability from this state to that state, based on what the agent thinks is the best thing to do, is 0.99. Now we have all of the elements needed to calculate the probability of a trajectory given a policy. Essentially what we're trying to calculate is, okay, let's draw some trajectory through this environment that we have. Given how the agent thinks, like if it gets some input, what's it going to do? One agent might always turn left when it sees a wall, when one agent might turn right when it sees a wall. A smarter agent might hop over the wall, right? Depending on what agent you select to put inside of that equation up there, like that pi stands for the policy, by the way, that's the agent, you will get a different probability of exploring a trajectory. The general idea is you have a trajectory and different policies or agents will give you different chances of exploring that trajectory. Does that make sense? And someone else tell me if it doesn't. This is on a conceptual level. Any questions? Anyone? Okay. So that is how you calculate the probability of trajectory, given you have a policy pi. And that's important because we use it in our next equation, right? Now I've proven that this can be somehow calculated. We're going to use it. Oh yeah, whoops. That's the trajectory. That's what it'll look like. So now we are going to calculate the expected return, right? And that uses that probability of a trajectory given a policy, right? So the general idea, and I won't go too much into what animation was here? Oh, yeah, the general idea is this. You could explore, just imagine you have some game and you're somehow able to know every single possible trajectory, right? Some of those trajectories are better than others. Maybe like 90 of them just put you in a ditch, right? But the other 10% of those trajectories maybe, make you win the game. And of those 10, maybe 1% of them are the optimal strategy to beat that game, right? The general idea is that those trajectories that let you beat the game efficiently should give you also the highest return, right? So if we have an agent that overall chooses the right trajectories more, then the expected return of that agent will be higher compared to an agent that chooses the bad things all the time, right? Say, just for the simplest case, there's two trajectories. One that gives you a reward of 5 and one that gives you a reward of 1, right? So you can, the integral right there, it theoretically means like all possible trajectories, but we're only going to be considering like the ones that we explore. So we have these two trajectories, right? One of them gives you a reward of 5 and one of them gives you a reward of 1. If you have an agent that takes the trajectory with the reward of 1, the lower one, with a probability of 0.99999, and the trajectory with the return of 5 with a probability of like 0.00001, you plug that into this equation and you'll see that the how good that agent is, that j of pi, is going to be low, because you're multiplying a number that's close to 1 with the lower number from that set, and you're multiplying the number that's close to 0 with the higher number for that set. The alternative is that you have an agent that selects the good trajectory way more often, with maybe a probability of just 1, right? And then you have 1 times 5. That'll return 5 versus while the other one returns 1. So therefore, the agent that chooses the trajectory that is more optimal will be selected by this algorithm, basically, right? Or not the algorithm, sorry, selected by this objective function. So the general idea is, if we formulate the problem like this, and we maximize j pi, then we will end up with an agent that takes trajectories that we want it to take. Any questions on that? There's got to be one. Mm-hmm. Oh, yeah. No, because this only considers, if you see on the left hand side of the equation, it's probability of tau given pi. Tau is the blue. This is tau, only the blue. So yeah, it only will consider what the agent actually did, if that makes sense. But then maybe it takes another trajectory the next time you initialize it, and then it goes on the orange path. Then that becomes tau, and then you average over that, and then you get j of pi. Basically, you optimize for an agent that maximizes the return. And like I said, this is all proxy, right? If maximizing the return solves your problem in the most efficient way, then you're good. The agent will maximize the return, and you'll also solve your maze in the most efficient way. Now, if the agent somehow finds a way to maximize reward and not solve your problem, it'll just do that, right? So that's why reward shaping is important, like I said before. And usually what you're doing is training one agent. I don't know if maybe you thought we're making like you could like trade a bunch of agents and then slowly filter down to like one that's doing well. Did I answer your question? You can ask it again. Feel free. In simple cases like brick breaker or pong, you do know the solution, right? You know move towards the ball. In more complicated cases like alpha tensor, tensor game, we don't know the solution. We set up everything properly and then trust that the agent will find something optimal. So it depends, basically. Yeah, it depends on your environment.
So is this equation in a sense to like optimize the different, like, because you have all these different policies that are trying to optimize the reward, and then is this solution like optimizing out of all the agents, which one is the best?
Yeah, basically. Or the when I've trained reinforcement learning models, there's one agent and it does it and it gets told how bad it does and then it updates its own parameters. So, and then it slowly learns to be better and better. Although you could do that in parallel with a bunch of agents and then kill off the ones that don't do as well. Basically, like if you use the j of pi as like we want to maximize this, you can either pick the agent that maximizes it, replicate it, and then try it again. Like that's genetic algorithms. Or you could change the weights of the one agent you have, and then that would also maximize the algorithm because then it would be a different pi, basically. Again, it depends. There's like a lot of ways to do this, right? Any other questions? Oh, are you asking how do we like maybe backprop or make the agents better? Oh, that's next. Yeah. I haven't gotten to actually how to optimize this. This is just I've gotten to what we're optimizing, by the way. Any questions? Yeah. Mm. No, because you could make some death condition like there is in the real world, right? Say, for example, you have a racetrack, only the furthest 10 cars get to reproduce. I don't know what that'd look like. Yeah, but yeah, only yeah. Anyway, yeah. Basically, you would just have like some kind of selection that could be automated. So you don't need to like say this is the best. You could like, here are the returns for each car, right? And then these are the cars with the top 10 returns. Let's take their networks and then like, shift their parameters around, and then you'll get better and better. Yeah. Anyone else? Are you familiar with temporal difference learning? No. Okay, I'm going to get into that in a little bit. Essentially, there is an idea of how surprising is this thing, and then that adjusts the parameters of the network. This is really cool. But yeah, this is all like just for like computers so far. I haven't gotten to like much of the neuroscience yet. Yeah. So and then ultimately, like what finally is here, when you see a star next to something, it tends to mean it's the optimal whatever it is. So if you find the policy pi that maximizes J, then you have found pi star, which means you found the optimal policy, right? That's just notation. So now we're getting into these things called Q functions, which are basically ultimately what we want, right? So this is the final, second to last layer of like complexity. So you have this idea of Q star, which I'll try and explain to the best of my ability. Q star is an algorithm such that if you were to give it like a state and an action, it's based off let me think about how to say this in the most concise way possible. This Q function, this Q star function, is essentially like omnipotent. You can think about it like, right? If you had this function, you could see for every state action pair, what is like the best action. You could basically take this state that you're in, check every action that you possibly have, and then select the one with the highest return or value for this Q star function, right? And then you'd be able to essentially just take that action, move to the next step, and then boom, you've made the most optimal step in your environment, right? So this is the optimal action value function, or the optimal Q function. And it says over there, gives you the expected return if you start in state S, take some arbitrary action A, and then forever act according to the optimal policy. So this assumes that you know the optimal policy. And again, this is theoretical. We are trying to get here. We're trying to estimate it using deep learning, but there's no real way to check if you ever actually have fully calculated like Q star, right? You can if you have a very simple state space and a very simple action space, but usually when you're applying deep reinforcement learning to a problem, you don't have that. So the general idea is, okay, we have Q star, we are trying to estimate it, so that if we have this algorithm, all we have to do is say, hey, Q star, here is a state, here's a bunch of actions, which one is gonna give me the best result? And then if it is really Q star, it'll tell you, take this action, and then take this action, take this, and then it'll help you solve the problem that you formulated. So we are trying to now, based on all the stuff I said, estimate Q star to the best of our ability.
So is Q star kind of going to be like how we can compare how well our reinforcement learning program is doing?
Almost. Yeah, it's not. We will never know Q star. It's like the ideal what we want to get to. This is more theoretical than the previous stuff I showed. This is like if we could act perfectly, here's what it would look like, right? So this is more just like a neat idea, right? Here, using all the formalization we had, how do we set up things such that we have the perfect Q function, right? And now how can we try and get there to the best of our abilities, right? So here's the general intuition I'm going to give before I go into the next step, which is one of the last parts I'm going to talk about. If Q star has some properties, and we optimize our algorithm to also have those properties, we can get closer to having our algorithm act like Q star. Okay? That's the general idea. Q star, this omnipotent function, will have some properties. It has this certain self-satisfiability property. And if we optimize for that, then we too can try and be like Q star. Okay? Okay, yeah. So this is what it is. It's the Bellman self-satisfiability equation, essentially. Now, this is a bit much, but I'm going to go over it on like a higher level. In fact, I'm not even sure if I need this slide. Yeah, I'll just go to this one, and then I'll go back if we need to review it. So again, read this here. Our current goal is to estimate Q star, right? Which is the Q function which that if used, we can maximize our expected return. Now, if you're wondering, okay, how does this work? Like, how do we make an actual agent? Well, the simplest way, and maybe this might help it make more sense, let's take you have a deep neural network with an input the same size as the state space and an output the same size as the action space. You give it a state, it pops out an action, right? That's our agent, right? And we're trying to get it to be like Q star, okay? And because of the universal approximation theorem with neural networks and nonlinear estimators, we know that it's theoretically possible. So we're trying to optimize it for it. So first, let's say we have this. Here's state S prime, and another one in the corner. Don't worry about that one. Our agent is currently right here, right? And then we have a reward for taking a state action pair that leads you to state S prime. And then after that, you'll have, a reward for taking S prime and some action in the next time step, A prime, and that'll give you a different reward. And now we have this framework in which the agent has already taken that action and is over there, right? So I'm just kind of making two little universes. One where our agent is here, and one where our agent is in that middle bubble, right? And so the idea is this. We are trying to satisfy this condition. The idea that the optimal Q function will tell you the truth about what is the best actions to take, right? And if you really need to stare at that equation, but if you stare at it long enough, it makes sense, I promise you. If you give it a state and an action, right, and you take that and you just say, what's the number that comes out of this Q value, Q function, right? Say it gives you some number like 10, right? And let's say we trust it and we take that action and end up in state S prime, right? Now what should happen is if I estimate in that new state and action that I ended up in, it should be like the rest of the equation. Like I'm here, I've moved to here, and now the Q function is estimating from here and beyond. So the equation from this point forward should be equal to the equation from this point forward plus the difference that we just moved on. And I'll show you that more visually. Using the Q function here should evaluate to being the same as using the Q function over there plus the reward from the jump we made, right? Because this Q function is estimating, like way down the line, how good is the state action pair, right? And if it's doing a good job, it should accurately estimate the reward that you get from this state action pair. And if it properly guesses it, then if you say, all right, give me the Q value here, give me the Q value there, their difference should just be the exact value that the reward is, meaning that it implicitly estimated the reward of that state action pair correctly. Yeah. That's the thing. The equation itself might seem a little recursive, but it's more like it steps forward. It's not. It's calling itself in the sense that there's another Q star there, but that's those S prime and A prime are one time step ahead. So it's you call it and then you call it like the next time step and then so on and so forth. Again, this is what we're estimating for. We don't actually do this because if you have like infinite like trajectories or a game that never ends, this will just go on forever. But the idea is if we can optimize to have this self-satisfiability condition, that means we have a proper Q star function. This is the part that I always struggle with teaching because I feel like it's just so abstract. But essentially, like if you have a function that can tell you like how good your future is based on a current action you're taking. How do you check that that oracle that you have is true? Well, what you do is you'd ask it, should I move left or right? Right? And it says you should move left. So then you move left. And then you check, how good do I feel? Well, I feel this good, right? Maybe this analogy is falling apart, but just stay with me. Stepping from here to here made me feel reward of 5, right? So now the difference in the rest of my steps should be 5 less than it was before because I've gotten my reward of 5, right? That's what I'm trying to get at here. If the Q function is behaving properly, it'll implicitly estimate the reward of the state action pair through this process. Please ask questions. This is like very complicated. Yeah.
So in this sort of equation here,
Mm-hmm.
We're doing it generally. So if you're in state A,
Mm-hmm.
you take action A, you don't know exactly what the next state is, right?
Not necessarily.
If it were deterministic, so like
Mm-hmm.
if you were in state A and taking action A would definitely move you on to a different state.
Yeah.
Then do you know how this function would simplify?
So if you actually, this kind of goes back. Remember we were talking about renormalization that one time. It's not the exact same thing, but okay, this is separate. But basically, if you have like a purely Markovian process, you make a matrix of transition probabilities, you diagonalize it, and then you put it to the power of like a really high number. It should converge on some stationary distribution. That is Q. That's basically like Q learning or some form of Q learning. Here, because we don't know that it's a direct like transition, that's why we have to try our best to guess. That's where the deep network comes in and does better estimations for us. If that makes sense. But otherwise, you could just make that matrix, diagonalize it, estimate like it to the power of whatever, right? And then you can like multiply it together again and then find out where you're going to end up, right? That would be technically one simplification of like solving this problem. This is written out this complicated because we don't really know where we're going to end up given an action, right? Yeah. Anyway, I'm almost done. What time is it? Okay, damn. So, any more questions on like this Bellman self-satisfiability condition? Yeah, for sure. So I will do this in a better way, right? You have a Q function that tells you, given this state in action, how your future will be laid out. But it doesn't tell you, take this list of states and actions. It tells you, take this now, and here is the reward you expect to see, right? In the future, right? So let's say I'm here at some starting position, and my Q function gives me 100. Like it returns 100. It just equals 100, right? And it also says move to that state, right? So I take the action, I hope I end up there, and oh, great, I do, right? And then I ask it again, what is my, expected return? Now it says 95. So it's changed by 5. If this R of SA was 5, then it did the right thing. Because it said 100, it told you to move there, right? You moved there as it said, and then you asked it again, it said 95. And you already got your reward of 5. So you're on track to, based on this one sample, get the rest of your expected returns correctly, and it won't lie to you. That's the idea.
So wait, then in that case, just on the slide, should it be using the Q function here minus RSA? Because like you already gained those points. So.
It's essentially like, so SA on the left side, right? And that's S prime A prime on the right side. That implies that you're 1 time step forward. You've already gained the reward. Therefore, the expected return for the rest of your trajectory should be lower because you've already gotten some reward, right? That's why it's plus. Because it's like, here I am now. I take an action, I get my reward. It's consumed, it's eaten up. Whatever I have left to get is less. But what I've already consumed plus what I have left should equal what I originally estimated, right? Yeah. Any more questions? There's one more slide. No, 3 more. Right. So now this is where it becomes like a little more concrete. How do we train this? Well, the general idea, and this is where TD learning comes in, right? We have our, now notice how there's no stars here anymore. This is actually our Q function, right? So we have this thing on the left, that's going to be our temporal difference loss. We have our estimation at S comma A, and then assuming we took that state action pair, we also know the reward for that state action pair, right? And the difference in what we estimated to be the truth, and on this right side, what actually happened with that ground truth reward is how off our Q value is, our Q function is. And this is temporal difference learning, and it actually comes from neuroscience. Because this is the general framework by which dopamine, because when it comes to dopamine and rewiring of the brain, there is an idea of a difference in what you expect versus what you see. And if there is a difference, a surprise in what you see versus what you got, then your brain updates itself to account for that surprise, so that next time there is no surprise and what it estimates and what it gets are the exact same. So that's where neuroscience ties in here. And I wish I could go in more because there's a lot more ties when it comes specifically to reinforcement learning. But then this would go on to 7 p.m. And I'm sure everyone would like that, but I can't do that. Does this make sense? Because it's kind of, this is what I've kind of been building up to, temporal difference learning. So the Q function, when you're doing this thing called, this is deep Q learning, the Q function basically is your deep neural network, right? It takes a state and action. It'll tell you like the general idea of like what you're doing, right? But here's the thing. Are you saying like, when you say it changes with each like step, are you saying that if I evaluate it on some state and evaluate it on a different state, that gives me different values? And that's true. Yeah. So like Q function, depending on S and A, will give you different values. Yeah. Any questions on TD learning? And I understand that this is a lot. I don't expect you all to digest this and understand it immediately. There are a lot of resources in Unit 6, and there are also like the notebook was hard to make, and I'm being PG here, right? Yeah, that was a lot, but it's really good, and I think it should give you like a general understanding if you really read the code on how like to actually make a deep Q learning agent. Right. So, any more questions on this? Yeah.
I'm trying to understand this, and using your analogy, like stepping, like for example, if you're at a starting point
Mm-hmm.
and you type you basically have this magical machine of Q,
Mm-hmm.
and you type your current state and the action you're going to take
Mm-hmm.
Q, and it says your best reward is 100.
Mm-hmm.
And then after taking a step to the left, for example,
Mm-hmm.
and you figure out you got 5 rewards,
Mm-hmm.
but for example, if at that place you type into Q again and it tells you that your optimal score is, for example, 96,
Mm-hmm.
then like that difference of 1 would be
That delta on the left hand. Yes, exactly. And that's the surprise. That's how off the estimation was, right? And hopefully you'll update the parameters of the network so that that gets towards 0. That's the idea. Yeah. Okay. This is okay. So that's all of the hard like math stuff for this lecture. Thank you for sitting with me through it. It's super cool if you like understand it, but I understand learning it can be difficult. So take some time with it, and you don't have a unit next week, so you can definitely sit with the content. But I'm gonna go over some problems because I've trying to introduce this as like a super cool, it can solve everything. But no, there's a lot of problems with deep Q learning. It converges super slowly. It's very unstable. It has unrealistic human-like performance. Like it won't act like a person would in that environment. And it also fails silently. Like it won't tell you that it's doing bad, but it'll do bad. Yeah, it definitely does that. I can tell you for a fact it does this, fail silently, and it's really annoying to debug. So, but and this little joke right here, if you read that and find it funny, like I don't know what to tell you. Like I found it funny and I was kind of sad. I was like, damn. But it's interesting. It's just the idea that they're trying to convey in this little like blog post message is that deep reinforcement learning, deep Q learning, without a lot of additional tricks, is really unstable. It like will only work in very specific conditions. It'll only work a certain amount of the time. Sometimes it'll like solve the problem perfectly, wonderfully, and then for the next 1,000 episodes of it trying to solve the problem, it won't get it another time. And you'd think, it can do it once, just save that. But sometimes, like, the base algorithm doesn't account for that. So there's problems to it, right? But yeah, you guys read that? It's funny, right? Yeah. Okay. Anyway, yeah. Bro, please. All right. Any questions on anything I said so far? Sorry. Oh, like it crawls to like the nearest sugar. Right. Interesting. We should talk about that. I'm not fully sure if that fully applies here, but I'm sure because it's like a biological network, there may be something like that going on. Okay, great. Yeah.
For kind of the last equation, like with training it,
Mm-hmm.
I just want to make sure I kind of got like the concept right. So essentially, we're finding the difference in what's expected versus what we got.
Yes.
And then we're using some calculus to minimize that difference.
Yeah. And how that's exactly done, you can see in the notebook. So yeah, there's definitely more on that. Yeah. I don't want to keep everyone here for too much longer. If you have any questions, feel free to talk to me. But yeah, I think that's everything for today. So thank you. I'll see y'all after break.